The next talk is by Tim French from the University of Western Australia, and he's going to be talking about proof theory for aleatoric logic. Please, Tim, take care of it.
Thanks, Guillermo, and thanks, Guillermo and Sasha, for organising and everyone for being here. So I'm talking about some work I've been doing over recent years, which has really come from, well, it started with a project I set computer science students where I was expecting a sort of theoretic logic approach, and they solved it much more efficiently with a, perhaps unsurprisingly, with probabilistic methods. But since then, I've been looking at kind of taking those methods and trying to build a reasonable logic around them. So aleatory logic developed facilitating reasoning in AI applications. And the idea really is to take a true or false proposition that you might have in propositional logic, or true or false predicates, and basically replace them with an aleatoric event, a roll of a dice or a flip of a coin. Okay, so every time you encounter a proposition, you evaluate some probability again. And this turns out to be quite interesting for reasoning in a lot of artificial intelligence applications, a lot of common sense reasoning or machine learning applications. So you might often have that sort of decision which requires you to make a judgment. If my paper submission is one unfavourable review, is it worth resubmitting to a particular conference, or these sort of things? This is a decision you have to make. You don't have the full set of facts. You might have some experience, but you've got very few data points to make that experience, but we all have to make these decisions. So this is the setting we're looking at. So the propositions are built from atoms, and we consider them just to be judgments. So you might judge whether or not it is raining. I mean, it could be demonstrably true, but in a room like this, we wouldn't really have any idea. We might know Sydney weather this time of year. It's not impossible. We might have judgments about the journal that we're submitting to, whether or not the handling editor is kind. I might look around the room, see how many people are looking up, how many people are looking at their phone, and make a judgment about whether or not the audience is interested at all in what I'm saying. So these are the sorts of things that we basically just suppose. They're not observations. We can't be given these completely, and they're not commitments either. So once we've decided on one, it's not unambiguously true. So in order to make a decision or to use this process, we sample judgments from this source according to some protocols. So if I imagine myself submitting to this journal, and if I'm doing this imagining with all the experience I've got, I imagine 3 times and I imagine it gets accepted twice, then I might decide to go through with the submission. Okay, that's the setting that we're looking at. So in order to build a logic around this and to have some proof and reasoning, we're going to use a probabilistic formula because we're thinking of propositions as dice roll, coin flips. So it is a probabilistic logic. And the basic elements we use are really the basic elements from a fuzzy product logic. So we have the atomic propositions, the judgments we're making, and we suppose that we've got a countable set of these atomic propositions. Once we've got 2 propositions, we can take their conjunction. So we suppose reviewer 1 likes a paper and reviewer 2 likes a paper. 2 judgments, we can put them together, and if they both hold, then their conjunction holds. And the negation. As normal, if we judge something to be so, then its negation is not so. Okay, so all of this is can be basically thought of as fuzzy logic, but fuzzy logic's a logic of vagueness. And we add in 2 new operators that really kind of capture the idea of putting these decision-making protocols together. The first one is an expectation operator. So what do we expect from 2 judgments? So this is basically if you think of it as a decision-making protocol, we flip a coin. If it comes up heads, we evaluate alpha. If it comes up tails, we evaluate beta. Okay? And assuming it's a fair coin, we're basically just taking the average of the probability of alpha and beta. Okay, so it's just giving us a non-deterministic choice or an even choice between alpha and beta. The second operator we use, now considering these as probabilities or as a decision-making protocol, is a fixed point operator. So given some proposition alpha that contains X, some atom X, the fixed point of X for alpha is equal to the proposition where basically you just substitute substitute X recursively for the fixed point of alpha. So it's a standard fixed point definition. But now in a probabilistic setting, so every time we evaluate the formula, we might look at different things because we've got non-deterministic choice and coin flips and these sort of things, and we apply the fixed point operator that way. The fixed point operator can be shown to be generally unique in almost all situations, given a syntactic condition. So X should only ever occur in at most one part of any conjunct. So I'll try and motivate that a bit more. So to summarize the language that we're looking at, we have atomic propositions, X, which are judgments, but semantically, we can just consider these as the roll of a dice. Every time you encounter one of these symbols in a formula, you flip the coin with a bias or you roll the dice to decide whether or not it holds. We have negations and conjunctions as normal. We have this expectation operator, which is just the average likelihood of the two propositions, alpha and beta, and this fixed point operation, which allows us to iterate through and make a decision. Okay, so this gives us a propositional style language, but now we're talking probabilistic. So every proposition comes with a probability associated. So just some examples of formulas. I'll have a bit of space to write on the slides, but it's going to work this setting. So the top one, this says the fixed point of the expectation of A, some proposition, and X. Okay. So in this case, we'd evaluate this A 50% of the time. The other 50% of the time we get X, which means we just substitute the whole formula back in. So then we flip the dice again. If it comes up heads, we evaluate A, otherwise we get X, so we keep on repeating this process. We're flipping a fair coin, so eventually it's going to come up heads. So this formula itself is just equivalent to A. So it kind of gives us a protocol for evaluating. This one down the bottom, a lot more complicated. We don't have the necessary abbreviations really, but this is basically an OR operation. Just got the standard De Morgan law there, where we have a fixed point operator, and we've now got these three choices. So there's basically four choices. We're flipping coins for all of these sort of things. In one of them, X or alpha. In two of them, X and not alpha. And in the last one, X. Okay. So in this rightmost branch, we're always just going to loop back and evaluate everything else. In these next two right branches, if alpha is not true, then we're going to go back and do X. And if alpha is true, this just returns false. So both of these branches will be false when alpha is true. In this branch here, this is X or alpha. If X or A, sorry. If A is true, then this is always going to be true because it's normal. If A is false, it's going to go back. So if we look at this statement now, looking at them as independent statements, one always loops back. The other two, these two, if A is true, it's going to return false. This one, if A is true, it's going to return true. So because A always has the same probability, evaluate it each time, there's a 1 in 3 chance of this formula returning true. So this formula, no matter what A is, has got the probability of 1/3. Okay, so now let's put some semantics around it. So we're talking about probabilities, and it is, like I said, from computer science students, so it's a very simple semantics that kind of makes sense for a lot of their projects. We have an interpretation or a belief function that for each one of our propositions gives us a probability, 0 to 1. An atomic proposition is just this probability. Negation is 1 minus A. Conjunction is independent. So every time we evaluate any proposition, it's an independent probabilistic event. So we can just multiply them together. Very simple. The expectation operator is just the average of two probabilities. And well, there's two ways of doing the fixed point operator. You can see it as this iterative process. We can substitute any probability P for X, and if when we substitute P for X, the evaluation of alpha gives us P again, we say that's the fixed point. That works almost everywhere, except where alpha is X. When alpha is X, then that's true for every P. So in that case, we just say we'll take a half. There it is. We can also do this functionally. We can treat all of these as polynomials because that's basically what we're doing with, well, or rational functions. So all of these operations, 1 minus, multiplication, taking the average, are all very simple polynomial operations. So the semantics are all polynomial functions over the set of variables, except for this one here, which requires us to do a division. So we've got a rational function here where we can say that if this function is equivalent to x, we just take a half. Otherwise, we substitute x for 0 and divide it by 1 plus f with x substituted for 0 minus x substituted for 1. I'm not going to derive that. I'll try and give you some visualizations for these novel operators. So first of all, for the expectation, it's just a linear function of two probabilities. So we've got alpha and beta on the x and y axes, and on the z axes, we've got the expectation of alpha and beta. And it's just basically a plane that's tilted, but that will allow us to calculate all the probabilities. The more interesting one is the fixed point operation. So we had that condition that said for any two conjuncts, x can only appear in one of them. Now the conjuncts are where things get multiplied together. So as long as we say that x isn't on both sides of a conjunct, that means that we're never going to have any quadratic cubic terms of x in this formula that we're looking at. So x is, if we ignore the rest of the atoms in the formula, but just consider the formula in terms of x, it's going to be linear in terms of that. So alpha in terms of x is going to be a straight line. And that's always going to cross the diagonal at some particular point. Okay. So this is where that idea of f of 0 and f of 1, you can do a little bit of maths and work out exactly what the intercept with the diagonal is going to be. Okay. So there's some interesting abbreviations. If we want half, we can just use the fixed point operator we've already seen. Third, it's a little bit easier once we add in a use half and a disjunct. We haven't got a sense of truth in the language yet. We haven't put true in there. True is an abbreviation for yes or some always positive, a fixed point, x or a half. So if we do that substitution over and over again, we're going to get a half or a half or a half. Eventually, it's going to always be true. Likewise, if we want false, we just keep on substituting for x and a half. And I should apologize, the abstract has a different one. This is a deconstructed version of the logic that appears in the abstract, which had this conditional if then else operator. So a ternary construct. If alpha, then beta, otherwise gamma. That's normally just alpha times beta plus 1 minus alpha times probability of gamma as a weighted sum. But we don't need a ternary operator. We can simulate it using the expectation operator and a fixed point. So it just basically creates what's called a Bernoulli race. So we try to see if alpha is true first, and if alpha is true, then we go beta. We flip a coin. And the other times we check to see if not alpha is true, and then we do gamma. And these two sides are going to basically occur in proportion of alpha and not alpha. So they'll give us the conditional. Right. Okay, so that's aleatoric. What we're interested in, well, that's aleatoric propositions. There is no logic there. There's no sense of truth or just described properties, they're judgments. For this to be a logic, at a logic meeting, we need a sense of truth. So an identity is a pair of propositions which says that these two propositions are equivalent. So we're saying alpha is equal to beta. It's a definitional statement. If we've got a set of identities, we call it a theory, and we say an identity is valid if for all different interpretations, all different belief sets, alpha equals beta. It's consistent if alpha equals beta for some belief set. So then we've got a set of valid identities. So double negation is valid. Commutativity of and is valid. This fixed point operation that we talked about is valid. We've got consistent but not valid things. So alpha equal or A equals not A. That's true if A equals a half. So it basically just constrains A to be equal a half. And we've got things which are not consistent. So true equals false is not satisfied in any interpretation. So now we've got a notion of logic, the equivalence of or the identity of two atoms. We can talk about satisfiability, completeness. And what we're going to focus on is just completeness of the valid identities. Okay? So the proof system, sorry, it's fairly hideous mass to absorb quickly, but it takes a lot of very familiar commutativity and associativity rules with a few of the standard things for fixed point operations, a transitivity operation, and substitution. So it's fairly standard, but it's also quite rare to get nice short axiomatizations for probabilistic logics. So what I'm going to do for the remaining time is talk about the completeness proof for this axiomatization. So quickly going through the rules, we have something should be identical to itself, commutativity and associativity, double negation. Negation distributes over this expectation operator. The expectation operator is commutative. And we also have that the expectation of something with itself is the same as itself, which makes a lot of sense. And distributes over expectation. We can swap terms in expectations. And we have the standard fixed point operators. The fixed point introduction operator, again, dealing with this situation where we don't fixed point X, we need to make sure that there is something that is not entirely X. So the standard fixed point introduction needs to make sure that X is not substituting into itself. Otherwise, we would say that anything equals fx of X, which is not what we want. There's some standard deductions there, but I don't think I'll have time to go through them. We might come back to them a little bit later. The main result I'd like to talk about is completeness for validity. And completeness for validity is different to completeness for theories. So completeness for validity, for every identity that's true in every interpretation, then we'd like a recursive axiomatization for that. Now, if I was given a theory to start with, and then I wanted to recursively generate every consequence of that theory, that's quite a different problem. If we've got implication in a logic, then they're basically the same. They often reduce to the exact same problem. But in this case, we don't have implication. All we've got is the identity operation. So there's no intrinsic implication. So they are actually quite different problems. And completeness for theories is quite a lot more difficult. But we are dealing with basically rational functions now. So we define a normal form for all aleatoric propositions and give a provable reduction to the normal form. There's some really nice results that give a correspondence between the normal form and the set of rational functions over A. And then if alpha equals beta is valid over all things, so they're functionally equivalent, then the two rational functions corresponding to them and the normal form are going to be equivalent. So that we can use that to reduce the expression of alpha to the expression of beta, basically just by using mathematical polynomial operations. So the expressivity results that make this work is a really nice result from Polya. Given any homogeneous and positive polynomial for sufficiently large n, if we multiply it by the sum of y to the power of n, all of the coefficients are positive, which is a really nice result. It doesn't seem really relevant here, but Moselle and Perez had a nice result where they looked at coin flipping polynomials, which are quite similar to the things we're talking about here. And the functions represented by the aleatoric propositions and the coin flipping polynomials that Moselle and Perez were looking at are exactly the set of rational functions from 0, 1 to 0, 1. So basically talking about mapping polynomials to one another. And that would be enough if we were just looking at two variables. For more than two variables, we need to make sure that they are only 0 or 1 on entire hyperfaces of the cube. Okay, so there are, for n equals 3 or bigger, cases where a probability just kisses the 0 in the middle of a hyperface, the edge of a cube or a n-dimensional cube, which then means that it doesn't work as a probability. But aside from all those cases, every single rational function corresponds to one of these propositions. So we can use these to have the functional expression corresponding to one of these probabilistic propositions as a rational function, where we've got these homogeneous rational function where we've got two polynomials. The AIs are always smaller than the BIs, and they're over a set of coefficients. And so we've now got an expression corresponding to the logical form. Now we can turn this logical form, or we can translate every aleatoric proposition into a normal form that mimics this polynomial equation. So we basically build it up layer by layer. At the bottom layer, we've got literals, propositions, and their negations. Then we've got conjunctions of literals. Then we've got, we call them disjuncts, but they've got this x, which is a fixed point variable, and there's only one fixed point variable we need, where we have x and the negation of a conjunct, or x with the disjunct of a conjunct, or just x itself. And then we take the expectation of all of these disjuncts. Okay, so, and a fixed point operator on top of all of that. So probably better to look at a picture representation of this. We've got the fixed point right at the top. Then we've got this expectation, which basically just gives us a tree. And because we've taken the disjuncts all at the same level, this basically just gives us a uniform distribution of all of these different, essentially conjuncts of literals. And so what we're basically doing is we're taking an even choice of any one of these conjuncts. And if it's an x or 1, If we flip all our coins, A comes true, B comes false, we get all the way to the bottom, then we say true. We accept it. If we don't get all the way to the bottom, then X gets in, we go back to the top and we try again. Okay? If we get one of these red ones, where it's an and, we end up picking this one, A comes true, then B is false, and we get all the way to the bottom, then we say false. Because we've negated this, it's X and this, and if all of these things are true, the negation's going to be false, so the conjunction's always going to be false, so we're just going to do false. Now, each one of these corresponds to a pattern of a term in the polynomial. AI corresponds to how many of these terms you see, because from Polya's result, because AI and BI are now positive integers, we're talking combinatorics. We're just counting how many of these different things turn up. And the BIs are the red ones and the blue ones together. So basically, how many of these, what's the probability of one of these paths being evaluated? And what's the probability of it being true over the probability of it being anything, is the question that we're answering. Okay? So that's a really nice characterization of the semantics for these operations. So the completeness proof basically involves translating every one of these propositions into something of this form. So it's big blow up in terms of the syntactic complexity, and then proving, because now we've got this rational function, homogeneous rational function representation, we can use number theory to find the most reduced form, the minimal form of that polynomial, and show that every one of these is equivalent to the minimal form of the polynomial. The minimal form of the polynomial is unique. So two equivalent propositions are going to be equivalent to a unique form. And from that, transitivity will give us that two functionally equivalent propositions are provably equivalent. Okay, so if anyone's seen stuff like this, please let me know. I mean, I've been talking to people and it's a bit fuzzy, but not really. It's not about vagueness. There's a lot of work on probabilistic logic, but they're reasoning about probabilities rather than reasoning probabilistically. Probabilities typically occur explicitly in the syntax. It does allow things that look like contradictions, but if we allow false equals true, then we still get the explosion problem in this logic. So it's not really like a paraconsistent logic, but it is very useful for a lot of the AI applications that I work with students. So it's quite interesting in that regard. And we are looking at, we do have first order extensions of this as well, which make it much more useful for things like learning, where you're actually able to reason about things and experience things and remember operations. But I'll stop there because I think it's morning time.
Stop the recording.